Antarctica is not an empty continent. It is a buried one. From the air, its interior appears almost featureless. A white horizon, a few dark ridges, and an ice sheet so vast that distance becomes difficult to judge. Yet the surface is only the uppermost layer of the landscape. Beneath it lies another Antarctica, concealed under an average of more than 2 kilometers of ice, and, in some places, nearly 5. That hidden terrain contains mountain ranges, deep basins, valleys cut by vanished rivers, sediment-filled lowlands, and water systems that move in darkness. For centuries, the unknown beneath Antarctica attracted stories. Hollow Earth legends, secret entrances, lost civilizations, and hidden bases all borrowed power from the same fact. Almost no one could see what was below. But the scientific answer is far more compelling than the mythology. There is no evidence for a habitable inner world beneath the continent. There is, however, a real continent under the ice, and researchers are still learning how to map it. The first challenge is simple to describe and extraordinarily difficult to solve. Ice hides rock. Satellites can measure the height and movement of the surface, but they cannot photograph the buried ground directly through several kilometers of frozen material. To recover the hidden landscape, scientists combine many kinds of evidence. Aircraft fly long, carefully planned lines over the ice sheet, while radar antennas send radio waves downward. Those signals travel through snow and ice, reflect from internal layers in the bed below, and return to receivers on the aircraft. The time required for the echo to return helps estimate ice thickness. Gravity and magnetic instruments add clues about the geology. Satellite measurements show surface elevation and ice velocity. Where radar lines are sparse, the physics of ice flow helps constrain what the unseen bed must look like. The result is not a photograph. It is a reconstruction built for measurement, calculation, and uncertainty. Modern products such as BedMachine Antarctica and BedMap3 merge decades of surveys into grid models of ice thickness, bed elevation, and surrounding seafloor. BedMap3 alone incorporated scores of newer airborne surveys, tens of millions of additional data points, and nearly 2 million line kilometers of measurements. BedMachine version 4 now applies updated methods and higher resolution inputs across the continent. Each generation removes part of the blank space, but none eliminates it completely. When the ice is digitally removed, the familiar white continent changes shape. East Antarctica emerges as a vast continental mass with high interior terrain. West Antarctica becomes a more fragmented world, much of it resting below sea level, divided by mountain blocks and deep marine basins. The bed is not a smooth platform. It is folded, fractured, carved, and drowned in places. Some ridges may slow retreating ice. Some inland sloping troughs can guide warm ocean water beneath glaciers. The hidden topography is not merely a curiosity. It controls how the ice moves. Near the center of East Antarctica lies one of the most dramatic discoveries, the Gamburtsev Subglacial Mountains. They are completely buried, yet their peaks and valleys form a range comparable in scale to major mountain systems above the ice. Airborne surveys revealed sharp ridges, deep valleys, and nearby lakes beneath several kilometers of frozen cover. The mountains were first detected during the International Geophysical Year, but only later surveys began to reveal their form. Their preservation is part of the mystery. Mountains exposed at the surface are continually attacked by wind, water, frost, and glaciers. The Gamburtsevs have remained sealed beneath a cold-based interior ice sheet that, in many locations, has been frozen to the bed and comparatively non-erosive. Ice hid the range, but it also helped protect its shape. Elsewhere, the buried terrain descends to astonishing depths. Beneath Denman Glacier, mapping revealed a trench that reaches roughly 3.5 kilometers below sea level, the deepest known continental point on Earth. The importance of that trough is not simply its record depth. Its geometry slopes inland, creating a possible pathway along which ocean-driven melting could influence the glacier. A single unseen valley can therefore matter to the future of global coastlines. But the terrain beneath Antarctica is older than the ice above it. In East Antarctica, researchers identified an extensive buried landscape organized into highland blocks and branching valleys. Its pattern resembles a river network formed before the modern ice sheet dominated the region. Later local glaciers modified parts of it, and major outlet glaciers cut deeper troughs around it. Yet broad surfaces survived. The age cannot be read like a date carved into stone. It is inferred from the landscape, the known history of Antarctic glaciation, and the evidence that large-scale erosive ice has not repeatedly swept across it. Researchers concluded that parts of this terrain likely predate the Middle Miocene and may have remained preserved for at least 14 million years, possibly much longer. This changes the meaning of the word hidden. The ice does not cover only mountains and basins. It covers a former surface of the planet, shaped under climates unlike the present. Water once moved through valleys now sealed in darkness. Vegetation once existed in Antarctica during warmer chapters of its history. The exact appearance of a particular buried valley cannot be reconstructed with certainty, but the drainage patterns reveal that the continent was not always the frozen world seen today. Then comes another surprise. Beneath a continent defined by ice, liquid water is widespread. At the base of the ice sheet, pressure lowers the melting point. Heat rises slowly from Earth's interior. Friction is produced where ice moves over rock and sediment. In some locations, these factors allow water to remain liquid even when the surface far above is intensely cold. The water can collect in depressions, spread through saturated sediment, or travel along pathways controlled by pressure and topography. Scientists once imagined many subglacial lakes as isolated reservoirs. Some are relatively stable, including immense Lake Vostok beneath East Antarctica. Others are active. They fill, drain, and refill, lifting or lowering the ice surface by amounts detectable from satellites. In 2025, analysis of a decade of cryosat, two measurements identified 85 previously unknown active lakes, raising the known active total to 231 and the broader catalog to more than 700 subglacial lakes. That does not mean more than 700 open caves filled with water. Most lake boundaries are inferred from radar reflectivity, bed geometry, and changes in surface elevation. Many are shallow water bodies under enormous pressure. Some may be connected in networks. When an upstream lake drains, a downstream lake may fill. Water can reduce friction at the bed, change the speed of ice, and eventually reach the ocean. The Ellsworth subglacial highlands offered an earlier example of how incomplete the map remained. A systematic radar analysis reported 33 previously uncharted lakes in one region of West Antarctica. Several confidence categories were used, from clear, mirror-like basal reflections to less distinct signatures. That distinction matters. A responsible map shows not only what scientists think is present, but how certain they are. The hidden water also raises a deeper question. Can life persist beneath the ice? In January 2013, the Wizard project used a clean hot water drilling system to access Subglacial Lake Whillans in West Antarctica. The lake lay beneath about 800 meters of ice. It was not a vast open chamber. At the sampling site, the water column was only around 2 meters deep, lying above sediment in a dynamic drainage system. Researchers lowered sterilized instruments through the borehole and recovered water and sediment. The samples contained cells and genetic material from a diverse microbial community. Measurements showed that the ecosystem was metabolically active. These organisms lived without sunlight, relying on chemical energy and nutrients associated with water, minerals, and sediments beneath the ice. This discovery did not reveal monsters, ancient humans, or a sealed prehistoric jungle. It revealed something scientifically more important: a functioning ecosystem in one of Earth's most inaccessible environments. Life had persisted beneath the ice sheet, separated from the atmosphere and the sun, within a cold, dark hydrological system. Lake Whillans also demonstrated the difficulty of exploration. Contamination had to be controlled. Equipment had to operate in extreme cold. The opening through the ice could not remain stable indefinitely. A single borehole sampled one small location in an immense hidden network. Every result was valuable, but no result justified assuming that all subglacial lakes are identical. Other lakes may differ in depth, chemistry, water residence time, connection to the ocean, geothermal setting, and available energy. Some may contain sparse communities. Some may be dominated by sediments rather than open water. Many have never been directly sampled. The phrase subglacial ecosystem, therefore, describes a category of possibilities, not one uniform world. These environments are also relevant beyond Earth. Icy moons such as Europa and Enceladus are thought to contain liquid water beneath frozen exteriors. Antarctica provides an imperfect but valuable terrestrial comparison, a place where instruments, drilling methods, contamination controls, and theories about life without sunlight can be tested. The comparison must remain cautious, but it expands the scientific significance of every Antarctic sample. The deepest reason to map the hidden continent, however, concerns the ice above it. Ice flows downhill under its own weight, but the bed determines where it accelerates, where it is pinned, and where water collects. A rough ridge can provide resistance. A smooth sedimentary basin can allow faster sliding. A deep trough opening toward the ocean can expose grounded ice to warm water. Subglacial lakes can drain, altering pressure and friction. The hidden landscape shapes the visible one. That is why better bed maps improve models of future sea level rise. If the geometry beneath a glacier is wrong, predictions of retreat may also be wrong. The new maps are more detailed than any before them, yet measurement coverage remains uneven. Some regions have dense radar lines. Others rely more heavily on interpolation and flow-based inference. The apparent precision of a colored map can conceal large differences in confidence. Antarctica, therefore, remains a continent of two realities. The first is the surface, bright, wind-scoured, and visible to satellites. The second is the bed, dark, ancient, what in places, and reconstructed through echoes. The myths imagined doors into another world. Science found no door. It found mountains larger than many exposed ranges, valleys deeper than expected, river landscapes preserved across geological time, water moving beneath kilometers of ice, and microbial life surviving without sunlight. The map is no longer blank, but it is not complete. And the greatest unexplored landscape on Earth may not lie at the edge of the world, but beneath it.